Okay, now let's go back to the case of the magnetic force exerted on a moving electric charge. We had this formula earlier in the chapter, F equals Q V cross B. We're now going to apply this formula to see how a charged particle in motion, when exposed to a magnetic field, will behave. One of the first things we noticed is that this force, unlike any force we've learned before, is always perpendicular to V, right? Because it's V cross B, so it's got to be perpendicular to both V and B. In particular, it is perpendicular to V. So, as the particle moves in a magnetic field, it always receives a force that's perpendicular to it, to its direction of motion. So it moves like that, and it gets a sidewise force. Okay? It's always being nudged to the side instead of being pushed forward or pulled backward. So intuitively, you know this force can only change the direction of motion. It will not make you go faster or slower. And we know this is true because, as you recall from Physics 1A, the power delivered by a force on a particle moving with velocity v is F dot v. So how much is F dot v equal to in this case? Well, F and v are perpendicular to each other, so F dot v is 0, right? It is 0, and therefore no power is delivered on this charged particle in motion by the magnetic field. In other words, the rate of doing work by the magnetic force on the particle is 0. No work is done on the particle as it moves under the influence of magnetic field. And therefore, we say the kinetic energy of this particle cannot change, right? Recall the work energy theorem, and therefore the speed cannot change. Okay? The magnetic force is only there to turn the particle around. It cannot make it go faster or slower. Okay? This is something we keep in mind. If you want to make the particle go faster or slower, you may use an electric force, but a magnetic force alone can never achieve that. Now, let's take a look at the special case when a particle moves in a direction that is perpendicular to the magnetic field. Okay, so we're looking at a case when V and B themselves are perpendicular to each other. Not only are they perpendicular to F, but V and B themselves are perpendicular. Okay, so a particle, so we have a magnetic field pointing into the page, okay, a uniform B field pointing into the page, and then we have a particle, assuming to be positively charged, moving with a velocity v perp, and that v perp, this perp means this velocity is perpendicular to the magnetic field. Okay, let's see what happens. First of all, the direction of the magnetic force exerted by the field on such a moving particle, V cross B. V points into the blackboard, into the page, and V is like that. So you use the right hand rule. V sticking in, V going this way, right? And B sticking into the paper, so V cross B points that way. Q being positive, V cross B gives you the positive direction of the magnetic force. So you see the magnetic force, therefore, points this way. Okay, this is the magnetic force. The magnetic force. And it's always perpendicular to the direction of motion. So as the particle turns around, the magnetic force also turns around, keeping a 90-degree angle from it. What kind of motion will this particle undergo with such a force that's always perpendicular to it? Well, we know the speed cannot change, but direction of motion will. As a matter of fact, you learn from Physics 1A, it will be moving in a circle at a uniform speed. Okay, this is uniform circular motion, as you recall. And we can easily find the radius of that circular motion. What is the radius of the path of this particle generated by such a magnetic force? Well, let's see here. The magnetic force has a magnitude, which is Q times V times B times sine of the angle between the two, which is 90 degrees. So this F, okay, this F. In particular, we're going to use a subscript B to denote this is the magnetic force. But this is the force responsible for it to move in a circle. In fact, this is the force pointing to the center of the circle, O, right here. And that means it is being used as the centripetal force, right, to fulfill the circular motion requirement. But we know the centripetal force has this following expression from Physics 1A. Mass times centripetal acceleration. Do you still remember the expression for the centripetal acceleration? V squared over R, R being the radius. Remember that? Okay, so when we equate the magnetic force with the centripetal force, we get QVB equals mv squared over r. So once again, QVB equals mv squared over r. And from that, we can find r. R equals to, okay, V, you cancel 1 power mv over QB. Okay, this is the radius of the circular path. Now we can write this expression in a couple of equivalent ways. One is I can write m over q. I can solve for or q over m. Let's write q over m. Let's see what that is equal to. Q over m equals what? V over RB. That's one thing we can do, right? Why are we interested in q over m? Well, this is so-called charge to mass ratio for that particle. The thing about the charge to mass ratio is that every kind of elementary particles, such as a proton, an electron, you name it, has its own value of the charge to mass ratio. Okay? There are no two kinds of particles with the exact same charge to mass ratio. So the charge to mass ratio really is a unique feature, is a unique signature of a certain type of particle, such as electron, such as proton. Okay? As long as it's charged. Otherwise, of course, the ratio will be 0. If we can measure the charge to mass ratio, then we can identify what kind of particle it is. And this can be achieved if we can somehow measure V, measure B, and measure R. So that actually is a way of measuring the charge to mass ratio, therefore identifying the particle. That's something we can do in the lab setup. In fact, one of the labs we're going to do, it's called fine beam tube. What that is we have a glass bulb. Okay, we have a glass bulb, and it's filled with helium gas. And then we introduce a beam of electrons. And also the glass bulb is exposed to a magnetic field, okay, to an electromagnetic field. And as a result, as the electrons enter the glass bulb filled with helium, it will be bent into a circle. Now, suppose the magnetic field points inward like this. The electrons are negative charged, so they're going to go backwards. Okay, they're going to go backwards. But still, they're going to bend into a circle. Now, the electrons themselves are not visible. However, I can make their path visible as these electrons make collisions with the helium atoms. They will impart their kinetic energy to the helium atoms through collision, and that kinetic energy will cause the helium atoms to be excited, therefore emitting light. So it's going to glow, okay? What you see, the glow really is just the helium atom producing light. And so you see a lit path, okay, that glows in the dark, and that will allow you to figure out the radius. Okay, you can actually see this path. So that's the radius, and the B field can be calculated based on the electrical current produced in it, and if we can also find V, okay, which can be done by figuring out how much is the acceleration voltage which accelerates these electrons. So we know all of these quantities, V, R, and B, and from that we can find Q over M. Then we can compare this with the standard value of Q over M for electrons to see whether or not this path is actually caused by electrons or some unknown particle. Okay, so this is a way of identifying elementary particles. Now, in reality, the velocity of a charged particle when it enters a magnetic field may not be always perpendicular to the B field. Okay, so in general, we can divide the velocity of a charged particle into two components. One is V perp, that is the part that's perpendicular to the B field, and the other is V parallel, that is the part that's parallel to the B field. Okay, and these two types of velocities will behave differently. Now, if a particle is moving parallel to the B field, okay, so V parallel, will that component velocity ever change when you apply a magnetic force on it? Well, the magnetic force can only apply to V perp, okay? Because look at V cross B. If this V is parallel to B, what is V cross B? 0, right? So there exists no force, okay, in a direction along the magnetic field, okay? Because the force has to be perpendicular to the B field. So in a direction parallel to the B field, there is no force, therefore there is no acceleration, and therefore there is no change to this component. So as a particle comes in with a velocity moving in the b direction, that velocity will never change. It keeps on moving in that direction with the same velocity. At the same time, the component of velocity is perpendicular to the b field, as you can see here, will be turned around. Okay, that component, the speed does not change. Okay, the magnitude doesn't change, but the direction will change. So what's going to happen in general is that a particle will be going at a uniform pace in one direction, that is perpendicular to the b field, and yet in the perpendicular direction it will move in a circle. So basically you have a circle that's advancing forward. Okay, that is called a helix. It's like this. Okay, that's the most general case how a particle moves in a magnetic field, and here is the direction of the b field. So in this is the direction of v parallel. That never changes, but perpendicular to it, you see, in other words, we look at it from this angle, you're going to see a whole bunch of circles, okay, as it turns round and round and round, and that's one typical circle you're going to see. So that's called a helix, okay? This path is called a helix. So what you see here is a special case of a helix when this component of the velocity is 0, okay? So all these helixes really just collapse into one circle. They do not go forward or backward because this velocity is 0. Okay, but in general, when you see a helix, you suspect that there's probably a charged particle moving in a magnetic field. Now, what we're going to do starting from now is going to look at a collection of important applications based on our knowledge of the magnetic force. Okay, of the magnetic force. One of the things we're going to look at is the Earth's magnetic field, the so-called terrestrial magnetic field. We know the Earth is a giant magnet, right? It produces a magnetic field, and if this is the rotation of the Earth, so this side, that's the Arctic region, that's the Antarctic region. So as you know, this is the magnetic south or geometrical or geographical north, and this is the geographical south or magnetic north. Okay, so you can imagine magnetic field lines from the Earth pointing out like that and pointing in. Actually, it's the other way around. I'm sorry. This is the magnetic south, right? So field lines are defined to point into magnetic south. Okay, and they point out of the magnetic north. That's just a definition. Okay, but anyhow, the important issue here is that the fields are stronger near the two poles, whether it's north pole and south pole. Okay, the fields are stronger near the two poles and the weaker around the equator, right? Weaker around the equator. So if you follow the distribution of field lines, okay, from one pole through the polar region, through the equatorial region, and going to the other pole, you're going to see a picture like this. As far as the intensity of the B field is concerned, you're going to see something like this. The field lines are closely packed together near the magnetic north pole and magnetic south pole, and they're further apart near the equator. Why? Because in the equatorial region, the field is weaker. The magnetic field is weaker. So you have a non-uniform magnetic field like this. Okay, it's like a, this is like a bottleneck. Here's another bottleneck. What can we say about a magnetic field distribution like that? Well, it turns out this has important consequences. Okay, this thing is called a magnetic bottle. A magnetic bottle. The magnetic bottle produced by the Earth's magnetic field is of pivotal importance in shielding us away from cosmic radiation. The Earth is constantly being bombarded by rays of basically high-speed charged particles from the universe. Okay, these are called cosmic rays. Okay, cosmic rays. So they're high-speed charged particles coming from all over the universe. And these high-speed particles can cause damage to living tissues. Okay, so they can be harmful to us. Now, in order for them to reach the surface of the Earth, however, they have to first pass through the magnetic region, okay, in the upper atmosphere and beyond, created by the Earth's magnetic field. Let's look at a typical such a typical particle is a high-speed charged particle. Being at a high speed and being charged, it will be subject to a significant amount of magnetic force, which is proportional to Q and proportional to speed. Okay, let's look at a typical particle. Let's say the particle moves like this. Okay, moves like this near the polar region, either North Pole and South Pole. So at this moment, it is moving. At this moment, it's moving into the paper. Okay, let's say it's positively charged, just for the sake of definitiveness. Take a look at the magnetic force exerted on it. The Earth's magnetic field goes like this, right? It's not straight lines, otherwise the field will be uniform. It's not uniform. So it's just like that. Okay, so QV cross B. V goes into the paper, and B goes that way. So what's the direction of V cross B? V cross B. Okay, you get a force. You get a magnetic force pointing like that. Okay. Like that. That's F. You see, it is perpendicular to both the velocity, which sticks into the paper, and the magnetic field at that moment, which is like that. So this is 90 degrees. Okay, you can imagine what happens when you have a force like that. Now that force can be decomposed into two directions. Okay, one is like this, the other is like that, right? This particular component of the force is perpendicular to the direction of motion, and what it can do is that it can support this helical motion, so it keeps on going in circles. Yet at the same time, you have a force pulling this particle towards the center of this magnetic bottle. In other words, towards what? Towards the equatorial region where the field is weaker. So you can imagine the particle starting from here, if it does a helical motion, okay, starting from here near the one of the poles, it goes faster and faster and faster as it gets to the pole. It gets into the equatorial region. But let's see what happens when it goes past the equator, going to the other side of the Earth. Okay, now it keeps on going in those helical paths. Let's say at that particular moment. Okay, let's see what happens. Okay, let's see what happens. Let's say at this moment it is going just like here. It is going into the paper. Okay, it is going into the paper. This time the magnetic field is pointing like that. Right? It's pointing like that. So V cross B, what do you get now? V is like that into the paper. B is like that. Okay, B is like that. So V cross B. V cross B. Don't you get a force that way? Okay, so you now get a force that way. The magnetic force, it's kind of symmetrical. Okay, but you see that force tends to push the particle back to the equator, right? See, before you pass the equator, you get a force pulling you to the equator. After that, you get a force pushing you back to the equator. So the particle will go faster and faster and faster in this direction until it passes through the equator, and then it's going to slow down, slow. So the path will look like this. Okay. How come these helixes are getting closer together? Because the particle moves slower in this direction and slower in this direction as it nears the two poles. That means the particle spends more of its time near the two poles, because that's where it cannot travel very fast in this direction, and yet it passes through the equatorial region quickly. Okay, so it will be reflected back and forth between the two poles. Okay, back and forth between the two poles. Instead of collapsing onto the surface of the Earth, which is not very desirable, what really happens is that this particle will travel, between the two poles like this. It spends a lot of time near this pole and near that pole, and it goes faster when it passes through the equatorial region. It is trapped between these two poles in the upper atmosphere or beyond. It will not crash, at least most of them will not crash onto the surface of the Earth. The magnetic field of the Earth pushes them back and forth, and these are high-speed particles with a lot of kinetic energy. As they spend a lot of time near the two poles, they have a lot of opportunity to collide with air molecules in this region, in the polar region, and as they do so, they pass energy to the air molecules, causing the air molecules to glow in the dark. Okay, because light can be emitted as these air molecules gets energy from the cosmic rays. This is of course something known as aurora borealis, or northern light. Okay, in fact, this happens not only in the Arctic region, it also happens in the Antarctica. Same deal, except most people see it in the Arctic region, where it's more accessible, relatively more accessible to people. This is what happens when you go to Alaska. Okay, during the winter time when the sky is relatively dark, you see beautiful light shows that lit up the sky, multicolors. This in fact is caused by these high-speed cosmic rays trapped by the Earth's magnetic field. They spend a lot of time over the skies of the Arctic region, causing this spectacular light show instead of crashing onto the surface of the Earth to cause harm to us. So the Earth's magnetic field actually does a good job protecting us from the harm of these cosmic rays. And so you have a region, going from one pole to the other, high above the Earth, both sides actually, okay, both sides, where there is a lot of cosmic particles trapped back and forth. This is called the Van Allen belt, or Van Allen radiation belt. So this is one thing that Earth's magnetic field can do, a positive thing it can do to protect us from cosmic radiation. All right. Magnetic